Okay, so today we are going to talk about the binomial model. We are going to estimate probabilities using it, and we're going to kind of work through a couple of different methods on how to approach this. Again, I'm going to show you how to do it basic table probabilities method, and then I'm going to show you how to use the formula and your calculator. Um, there are benefits to all of them, but I will say it does take a little bit longer to go the route of finding the probability distribution table and then using that. But it kind of pros and cons of every method. So, one thing we have to know about the binomial distribution is there are many experiments and situations that result in what are called dichotomous responses. Now, here is just a general term for what we kind of do. More than likely in AP Stat setting, we call them Bernoulli trials. Basically, that means there's two possible choices: yes, no, true, false, heads, not heads. Two options. That's all you get. You don't have more than two outcomes available to you in a scenario. And a simple example is tossing a coin, where there are only two possibilities, heads or tails. There are many other types of experiments similar to a coin toss where you are observing the success or failure of a certain outcome. We call these binomial distributions, basically two options. That's all you got. And that's one of the big key things that you will be checking as you start to identify these binomial distributions. So there are four conditions that we have to consider and that have to be present in order for us to do a binomial model. Again, you want to make sure you have two categories. We call them success or failure. One thing that I do always mention is a success is not necessarily always positive. Say, for instance, you are doing research on a cancer patient, and your idea of success in this experiment is identifying someone who has cancer. Just because we personally think it's not considered a success, we have to think of it in terms of the model. It's a success to find somebody with cancer. We need a fixed number of observations. We have to know how many times are they tossing the coin? How many times are they rolling the dice? How many people are they picking from the student body? It has to be a fixed number. It's not a situation where you pick until you find somebody. That doesn't happen here. That's the other model. Here, you know how many times you're doing it. The observations are going to be independent. Basically, you want to make sure that one observation does not influence another. We've kind of gone with independence in pretty much everything we do since we started inference testing. We don't want any outside influence, any bias in these situations. And you want to have the probability is the same for each observation. And this kind of goes hand in hand with independent. I don't want my probabilities to change just because something occurred. A good example of this is cards. If I were doing a binomial model, it would require me to put back every card that I draw and reshuffle. I couldn't just keep pulling cards and not returning them because that would change my probabilities of getting a red card or a black card. So we have to have two categories, fixed number, independent, probabilities are the same. Those four things are required for a binomial experiment. Now, describing a binomial distribution, the distribution of the count x, and again, we talk about probabilities in terms of capital letters with parameters n and p, and it's the possible values of x are the integers from 0 to n. We're always going to start our x, our outcomes, with 0, and we're going to go until our end of fixed number trials. And we say x such that b is going to stand for binomial, n is our number, there we go, number of trials, and p is our probability of success. So x is our random variable, b is our binomial model, trials, success, probability. And this is something they may use on the AP exam. They may have something where they describe to you a binomial distribution and you kind of have to put it together, they may present that information in this manner. More than likely, they'll just give it to you in words and the context of the situation, but I always like to show it to you just in case. So, example 1. For the following examples, determine if they are a binomial setting or not. Explain why. So I'm going to kind of go down our list of what we checked for a binomial distribution and make sure that all of them have all 4 different qualities. So for A, we are tossing 20 coins and counting the number of heads. So we're interested in heads. That means my success fail works. I either have a heads or I don't. Heads, no heads. My second one is, do I have a fixed number of trials? Well, I'm tossing 20 coins. That means my N would be 20. It's fixed. I'm not going to keep tossing until I get 17 heads, nothing like that. I'm tossing all 20 every single time. I also know that my coins are going to be independent. Just because I toss one and I get a heads, that does not necessarily mean the next one is going to be tails. And another great thing about coins is the probability is going to be the same. Consistently, in the long run, it's going to be a 50-50 split between heads and tails. So with all 4 of these things happening, we do have a binomial model. Now let's go ahead and look at B. Picking 5 cards from a standard deck and counting the number of hearts, we replace the card each time and reshuffle. So first, I have hearts, no hearts. That's my success fail. I know that I'm picking 5 cards, so my N is going to be 5. And again, like with coins, my drawing of a card with the fact that I went in and I replaced and I reshuffled, I can say the cards are independent. I'm not influencing one by drawing a card, returning it, and reshuffling the deck. And because of that, we're going to say our probability of getting a hearts is 0.25 because that is one suit out of 4 different ones in a standard deck of cards. So this is also a binomial model. Looking at example C, picking 5 cards from a standard deck and counting the number of hearts without reshuffling. So I have picked 5 cards and I have not returned them, not reshuffled them, giving me cause for concern. Yes, I do have the fact that it is success fail, hearts, no hearts. And then I do have a fixed number of trials. I am picking 5. However, they're not independent. Once I pick it and I do not return, that alters my probabilities of picking another hearts. So, because of that, this is a not binomial. And most of the time, you could make the argument of it's not independent and it's not a consistent probability. Either one of those suffices. So if you were to say the probabilities change because we are not returning the cards and reshuffling the deck, that's just as correct as saying they're not independent. Choosing a card from a standard deck until you get a heart. Well, we know we do have success fail, heart, no hearts. However, we do not have a fixed number of trials. We are picking until we get a heart. That could be 2 cards, that could be 10 cards, it could be 12 cards, it could be anything. There's no fixed number of trials. Because of that, this is not binomial. So we want to know in the long run, how many cards am I expecting to pick? How many coins am I expecting to toss? That is the big, big key difference in what we're doing in binomial today and what we'll be doing in geometric on Wednesday. So for these, we are just identifying the different features of a binomial distribution. Now we're going to actually approach a problem in the standard way we've done so far using probability distribution. So let's go ahead and look at example 2 on the next page. I have Calvin. He's about to take a quiz, 5 questions, true, false, and he's not prepared. So he's going to guess on all 5 questions. Listed below are all the possible combinations of correct and incorrect responses on this quiz. Create a probability distribution where X is the number of correct responses. So the beneficial thing here is we have the possible combinations given to us. Now, more than likely, that will not be the case on the AP exam. They will just tell you there's 5 questions. He could get it right, he could get it wrong. And you would have to build out these combinations. That is time consuming. And that's kind of my big con for doing it this way is you might miss some. But for now, we do have these, so we're going to work with what we got. So I know that there are 5 questions, and we want to know how many correct responses he could get. So I know the first thing that could happen is he could get none. No correct responses whatsoever on the quiz. So that is one outcome out of my 4 times 8, my 32. So I have 1 over 32 for x equals 0. Then we move on to the possibility that he could get 1 correct. So I'm looking for one single C, and those are 5 out of 32. And then we look for the possibility he could get 2 correct, gets a little bit bigger. That gives me 10 outcomes. And then for the possibility that he could get 3 correct, we have, again, 10. And this starts to look the same on the other side. Possibility he could get 4 would give me another 5 out of 32. And the possibility that he gets them all correct, all 5, is 1 out of 32. And again, time consuming because you would have to go through every single outcome and kind of put it in a different category. But the nice thing about putting the work into the table is once it's done, it makes the probabilities a lot easier to just look at and see and find. So we have our probability distribution. What is the probability that he gets all the answers correct? So all the answers correct would mean x is equal to 5. So the probability that x is equal to 5 is 1 over 32. What's the probability he gets all the answers wrong? Well, if he was getting them all correct at 5, all of them wrong is 0. So probability of x is equal to 0 is 1 over 32. And then what is the probability that he gets exactly 3 answers correct? So x is equal to 3, which is 10 over 32. The nice thing about our AP exam is they do not require you to simplify your fractions. So it would be absolutely okay to leave this as 10 over 32. And what is the probability that he will pass the quiz? So passing the quiz is going to be getting at least 3 out of 5 or more correct. That's what we're going to say. We're going to say a D is going to pass for Calvin. We're going to be a little nice to him today. Generally, college rule, most likely, depending on your professor. So we have the probability that x is greater than or equal to 3, which if you recall from what we did with probability distributions at the beginning, all we have to do is take each individual probability and add them together. Probability of x is equal to 3 plus probability of x is equal to 4 plus probability of x is equal to 5, which I just take all of those fractions, add them together, and that's going to give me 16 out of 32 or 1/2. There's a 50% chance he will pass the test. Another thing that you might encounter is what's the probability that he gets 2 correct or 4 correct? And that would just be something similar to this where we add the probability of x is equal to 2 plus the probability of x is equal to 4. Kind of pulling back in on those probability rules we did before spring break. Now, this is just the standard approach using probability distributions tables. It definitely works, But again, you do have to be careful because more than likely they will not list all of the combinations for you. So you would have to go through and build that out, which does take time and it is tricky because there really is no rhyme or reason to creating those combinations, especially when you get up to really, really large number of trials. So what can we do instead of having to build out the combinations? Well, there is a formula we can use. And if X has a binomial distribution with n observations and a probability P on each observation, the possible values of X start at 0, go up to n, which is the number of trials. So we can say that the formula, which I'm going to pull up really quick, the probability of X is equal to K is equal to nk, which is a combination, which we'll talk about in a second, n combination k, p to the power of k, 1 minus p, n minus k with an exponent. So I'm going to kind of break this down into pieces and explain what this formula is actually doing. So again, we're interested in the probability of k successes. Then we want to see the combination. How many combinations from my number of trials result in a specific number of successes that I'm interested in? So combination of k successes and n trials. And the nice thing about this is we do have a formula for it, and there is a way to do it in your calculator. It requires factorials, a little bit of a lengthier process, but the nice thing is we can do this in our calculator on its own without even having to look at the factorial formula. But I do like to give it to you. So we take that however many combinations we have, we multiply it by the probability of success raised to the number of successes. So it's kind of like us doing the general multiplication rule. If I want to see 3 successes, I would take my probability and multiply it times itself 3 times. Now, again, we have to also think of, okay, I wanted 3 successes. Potentially that meant if my n was 5, I had 2 failures. So that's why I have 1 minus p, which is my probability of failure, to the power of however many failures would happen in that occurrence. So we're kind of taking combinations times successes times failures to get our probability of success. Now, this formula is specific to binomial distributions. We will only use this when we are talking about situations where there is a success fail, where there's a fixed number of trials, independence, probability is the same. And I kind of went in and gave you a little key as to what each variable means. And there is a small little tidbit on how to do combinations in your calculator. It's a menu to math, probability, number 3. Now, most of the newer calculators will give you a prompt that will show you where to fill in your values. A lot of the time you may just have to type in your number to begin with. You'll have to type in without the boxes, which I'll show you in a second. We're going to do an example, but I'm going to give you a little bit of time to copy this down. And I do want to say, of course, anything we do in stats, there's a way to do it through the formula, and there's a way to do it in your calculator. So yes, the formula is going to require some calculator work, but that's not going to be our only option. We will have a calculator function that helps us, but formula is given to you on the formula chart, so it's always nice to know how to use it. Okay, I'm going to go ahead and go on, but I can come back to this at the end if anyone needs to see it still. Let's go ahead and look at our setting again. So we're going to still be working with Calvin and his 5-question quiz. Just a reminder, we're interested in binary trials. Now, the little acronym that they use for binomial distribution is called BINS. It's the easiest way to kind of check that everything's there. You want binary, 2 outcomes, independent. They have to be independent of each other. The number of trials has to be fixed. This is the one I'm a little iffy with because it's used in both almost. And same probability throughout. So just again, reiterating that we need all 4 of these things for it to be considered a binomial setting. So let's check this for Calvin's quiz. Yes, we do have a binary trial. It's correct, or his answer is not correct. The guesses are going to be independent. Him guessing one correct is not going to influence another. We do have a fixed number of trials, n is going to be equal to 5. And because he did no studying and is completely guessing on true false, probability of success is 50%, whereas probability of failure is also 50%. So, say for instance, that's all we knew. We didn't have our outcomes, we didn't have our table, we had nothing else. And we wanted to find the probability that he gets exactly 3 correct. So I'm going to do this based on the formula we just had, which I can rewrite here. Probability of x is equal to k, n, k, n minus k. Let me double check all my variables are correct. I'm pretty sure. Yep, there we go. Okay, so we want to know the probability that x is equal to 3. So I just went ahead and plugged in my numbers into this formula. We know that n is equal to 5, so everywhere I saw an n, I put 5. And we know we're interested in k, 3 successes. So I put 5, 3. We have his probability of success of 0.5 raised to the power of 3, because that's the number of successes I want. Probability of failure, which is also 0.5 raised to a power of 2, because 5 minus 3 is 2. One thing that you can always do to check with this formula is these 2 exponents should add to be your number of trials. 3 plus 2, my 5 trials. So now let's go ahead and try this in our calculator. So I'm going to open up my calculator really quick, and I'm going to kind of show you how to do the combination function. So I'm going to go to math. Let's make this bigger. To math, I'm going to go over to probability, and it should be option number 3, NCR. So I'm going to go down to number 3. I'm going to hit enter. Now, my calculator is giving me a prompt for the subscripts. Maybe your calculator does not, which we'll talk about in a quick second. So I'm going to say 5 trials. I want 3 successes. And it's telling me there's 10 combinations that do that. Now, if your calculator did not have that prompt, what we've kind of found works is you type in your number of trials first, then you would go to math, probability, number 3, and it would place something there that says NCR, and then you would type your number of successes. So you just have to kind of do that part manually if you don't happen to have that prompt. So I know that it's 10 combinations, so I'm just going to plug that into my formula. 10 combinations, and then I'm going to have 0.5 to the power of 3. Oops, let's move this over. There we go. And then I'm going to have 0.5 to the power of 2, and then going to enter, and that's going to give me 0.3152, which if I put this in fraction form, is going to be 5 out of 16, which is coming from our 10 out of 32 that we got using the table. But for this one, you don't have to convert it to a fraction. I left mine as just 0.3152. I just kind of wanted to show you it's the same answer we got when we did the table looking at all of the combinations. So, what is the probability that Calvin will pass the quiz? So again, I'm going to follow that same method. Probability that x is greater than or equal to 3. We're going to add all 3 situations together. I already know the probability of x is equal to 3, but I do need to do the probability that x is equal to 4. So I did 5 trials, 4 successes, 0.5 to the power of 4, 0.5 to the power of 1. Both of these add up to 5. 5 trials, 5 successes, 0.5 to the power of 5, 0.5 to the power of 0. And that's going to give me 5 plus 0 is 0. Now, I'm not going to go through this whole thing in my calculator, but I do kind of want to show you one more time how to do combinations. I'm going to go to math, probability, down to number 3. So for my x is equal to 4, I have 5 trials and there are 4 successes. So that means 5 combinations result in this happening. And then if I wanted to know for my other one, which we already know there's only one instance, so let's make sure it's right, where I have 5 trials, 5 successes, should result in 1. So I would plug in 5 here, 1 here, and then I would get 50%, which is exactly what we got when we did it in the table. This is also really nice and helpful if you encounter a question where they ask you, how many combinations result in 2 successes? And they just want to know how many combinations. You would just go in 5, choose 2. Now that definitely decreased time, so you didn't have to list out all of the combinations, but there is a way to do it a little quicker in your calculator. So binomials in the calculator. On your calculator, we have a lot of distributions. We've dealt with normal CDF, we've dealt with TCDF. There is another one that we're going to use, and it's called our binom PDF CDF. You get these by going to second vars, and then option A should be binom PDF. Option B should be binom CDF. Now, everything we did with normal distributions and T distributions and chi-square distributions all were CDFs because of the nature of it being a density curve. Here, we do have instances where it can be exactly a value. That's why we are going to also consider PDFs for probability distributions. So, PDF is when it's P x is equal to a number, equal to only, exactly one number. We're going to go to binom PDF, which is option A. And so, what is the probability Calvin gets exactly 3 correct? So I'm going to pull up my calculator one more time, and then I'm going to show you where to go. So we're going to go to second, vars, all the way down to binom PDF, which is A. And it's if you have the prompts, you're just going to fill in the prompts. If you don't, you'll just do the commas. So we'll do trials PX, which I'll show you as I write it out. We had 5 trials. Probability of success was 0.5, and we are interested in exactly 3. X value, K value is the same thing. And we hit paste, and I get 0.3125, which is exactly what I did using the table and using the formula. Now, if your calculator happened to not have the prompts, it's just going to give you binom PDF with the open parentheses. All you would do is type 5, comma, 0.5, comma, 3, and it should still give you the answer. It's just you have to do it without the prompts. So for PDFs, we do exactly a value. CDF is cumulative, which means we're going to have a interval of values. Basically, you have an inequality, less than or equal to. And something to always remember is your inequalities are going to matter because of the inclusion or the exclusion of that last value. So, binom CDF, again, we are doing something a little bit different here, which I have a note to kind of remind us. Inequalities matter. The thing you have to be aware of is your calculator can only do less than or equal to. That's all it's going to work with. So you have to kind of convert your inequalities so that it fixes itself and gets what you actually want. Because if I want probability that Calvin will pass, that's the probability that x is greater than or equal to 3. My calculator is only doing less than or equal to. So if I want 3, 4, and 5, I need to consider the other side. And that's the only way I can make this work. Because remember, all of my probabilities add up to 100% or 1. So if I'm interested in the probability of x is equal to 3 plus 4 plus 5, what I can do instead is 1 minus the probability of x is less than or equal to 2. So that's what I'm going to do in my calculator. Going to open it up. We're going to go to second vars to B this time, binom CDF, 5 trials, 0.5 probability, and I want 2 or less. And then I'm going to do 1 minus 0.5, which is just 0.5. And similar to what we did with normal CDFs, yes, you do have to write out your calculator input for these types of problems to get credit. So that's why I have trials 5, P 0.5, X2. Yes, you have to label each individual value. One thing that I do suggest if you are unsure of what you're looking for, I always like to either write out the table, which is something I'll do in the next example, or I write out my outcomes. So we know that there were 0, 1, 2, 3, 4, 5. So I wanted 3 or greater, which meant the only thing I could do was find the probability of x is less than or equal to 2 and subtract 1 from it. Number lines help just to kind of organize the information. It's always going to be whole numbers. It's always going to start at 0. It's always going to go up to your desired or stated number of trials. So, calculator method. We have table, we have formula, we have calculator. Many, many methods for probability distributions. Now, let's just do a couple of examples. Probability given x is binomial with 5 trials and a 0.4 probability of success. Again, I like to kind of set up my table in a way so that I kind of know what numbers are included, not included. Most of the time, I don't do a full-blown table. I'll do a number line similar to what I just did for the previous example, but basically know where your numbers start, know where they end, and then we're just going to kind of try out some probabilities. So I want the probability that x is less than or equal to 1. So I'm going to do binom CDF because it's an inequality, not PDF. My trials is going to be 5. Probability of success is going to be 0.4. And because it's less than or equal to, I just have to enter the exact value of 1. And I'm going to do the first one with you, and then the rest will kind of just give you so we can kind of save on some time. Second vars, I'm doing binom CDF, and I have 5 trials, 0.4 success, and I want 1 or fewer. And that gives me 0.33696, which I think I just wrote out all 5 decimal places. Yes. So first probability. Second one, probability that x is less than 3. Notice that I don't have equal to, so I have to think of the fact if I want everything less than 3, really I want 0, 1, and 2. So I'm going to do binom CDF, where I have 5 trials, 0.4 probability of success, and 2 or fewer. So this will count, when I say x is 2, it's going to count 0, 1, and 2. And that's the same thing as x is less than 3. Put that into my calculator, and I get 0.68256. For C and D, we have to be a little bit careful because notice we're saying x is greater than or equal to 4. So that would be 4 and 5. But I can't do greater than in my calculator. So I need to do 1 minus the probability of x is less than or equal to 3. So since I want 4 and 5, I have to get everything less than that in order to get the true probability. So I do 1 minus CDF because it is an inequality, 5 trials, 0.4 probability, and I want to be 3 or less. So that's going to count 3, 2, 1, and 0, which gives me 0.08704. Now, D is one you can approach in a very different way than what I did in my notes, but I was going for it. Probability that x is greater than 4. The only instance where probability is x is greater than 4 is 5. So your other option, besides what I do, is you could just do probability that x is equal to 5. I went ahead and did 1 minus the binom CDF with 5 trials, 0.4 probability, 4 successes, and that gave me 0.01024, which would give me the same exact value if I were to plug in PDF for 5 successes. Now, the last little bit we're going to talk about, not going to take us long at all, is mean and standard deviation. Sometimes they do ask you, what's the expected value for this probability distribution? We use a little bit different formulas because we will not be generating that table most likely. So all you have to do is take your number of trials, multiply it times your probability, and then square root of NP times 1 minus P. So we have, what is the expected value for Calvin's quiz? So all I have to do is take my number of trials 5 times my probability of success 0.5, which is 2.5. So if Calvin took many of these quizzes, we would expect him to get 2.5 correct. For standard deviation, I'm just plugging in trials, success, fail. So 5.5 and 0.5, taking the square root of it. Typical deviation from the expected value is 1.1180. Question's correct. So we can say around, if I add that and subtract it from the mean, that's kind of typically how much I would expect him to vary in numerous trials. And the last one is asking us the question, suppose the probability any random freshman girl will agree to try out for Desperados is 0.1, and Mr. Esparza is asking 20 random girls to try out. What is the probability that A, exactly 1 will say yes? So this, I'm just going to go straight to my calculator. I want the probability. First let's define X to be number of girls who say yes. And I just kind of describe my distribution here. Not necessary, but again, just so you can see that language. Probability that X is equal to 1. If it's equal to, I want to do binom PDF. So binom PDF, 20 trials, 0.10 probability of success. I want 1 success, and my calculator told me that was 0.2702. What's the probability that at least 1 will say yes? So I'm interested in the probability that X is, which now that I'm thinking about this, I did 1 or less, but we'll make it work. Probability that at least 1. This should be this way. We'll say yes. So in my actual problem, I need to fix it. It should be 1 minus the binom CDF, where I can get everything less than 1, which is 1 minus 0.3917, which is 0.6083. I caught it as soon as I saw it. And then expected value and standard deviation are super easy. We're just going to plug in N and P, 20 trials, 0.10 probability of success. We'd expect about 2 people to say yes. And standard deviation, trials, success, fail. And that 2 will typically vary by 1.3416. And that takes care of example 5. Now, it was a lot of information. However, front loading all of this makes geometric on Wednesday a lot easier for us.